But suffice it to say, make sure that when you're doing work in this class that your calculator is in degree mode and not radian mode. We won't actually be needing it today. So I noticed a bunch of you grabbed your calculator right away to check, but it is always a good idea. And unless you take a 30 level math class, either 30-2 or 30-1, that's always going to be the case. You never want to be in radian mode. So I'm giving you this graphic because, believe it or not, when we make multiple choice questions, we make some of the choices that are incorrect, choices that a student would get if they did the work properly but were in the wrong mode, which is really dirty. It's very dirty, but we do that, and so does the diploma exam. So it's your responsibility to make sure you're working in degrees. We are going to be, in this unit, looking at three main things. Understanding rotation angles. And when we talk, this is actually on the front cover page, these things. When we talk about angles in standard position or rotation angles, that's going to be different than something which is called, for example, a reference angle. So a lot of what this unit is about is terminology, because if you don't understand the terminology, you won't understand what the question is asking. It's not that I'm going to ask you to write out definitions on an exam, but you need to know the definitions to understand the problems. Then we're going to be looking at the three primary trigonometric ratios: sine of an angle, cosine of an angle, and tangent of an angle. But we are going to be looking at rotation angles in those ratios past 90 degrees. So we're going to be talking about the meaning of something like, for example, the sine of 330 degrees, which happens to be 0.5. There's a significance to that. And what that means is we're not always talking about triangles. Because if I say to you, we want to talk about, as an illustration, the sine of 330 degrees, you cannot have a triangle with an angle, an interior angle of 330 degrees. It doesn't make sense. And this is the weird thing, because trigonometry, you're used to, oh, it's triangles. Opposite, adjacent, hypotenuse. Well, it goes beyond that. So we're going to be looking at larger angles. And we're going to be solving problems that do involve triangles. These involve triangles. But these triangles will not contain a right angle. And what that means is if I give you a triangle and we have to solve that triangle, or we have to find some missing sides or angles of the triangle, if there's no right angle, there's no hypotenuse. And if there's no hypotenuse, you can't use sine equals opposite over hypotenuse. It just doesn't work because there's no hypotenuse. You can't use tangent equals opposite over adjacent because there is no opposite and adjacent in one of these triangles. So in order to work with those triangles, we use what's called the cosine law and the sine law, which are not what you've learned in the past. There's something different. Incidentally, there is a cosine law for these triangles. There's a sine law for these triangles, but there's no tangent law. We don't use a tangent law. So now on page 1 of your unit handout, this is what we're doing today. As I said, this is a very, very, very light topic today. You will need a ruler, not to measure anything, but to draw some straight lines. You're welcome. If we take a look at the objectives, you have to be able to identify and sketch angles in what are called standard position. And then if you look at the other two bullets and you read them carefully, you'll understand that there are two types of angles we're learning about today. One is called a reference angle and one is called a rotation angle. And if you have a reference angle, oh, you already got one? If you have a reference angle, then you can calculate a rotation angle. And if you have a rotation angle, you can calculate or determine the reference angle. So there's a difference between rotation angles and reference angles. And I better clear this up right now, that whenever we talk about an angle in standard position, This is what we call a rotation angle. So I'm going to be using most likely the phrase rotation angle, but you might see in your textbook or your notes angle in standard position. They mean the same thing. But a reference angle is something different. This is different than a rotation angle. We'll see there's a case where it might be equal to the rotation angle, but in terms of what a reference angle is, it's different than a rotation angle. So that's our objectives for today. We're dealing here in this unit with what's called coordinate trigonometry, as opposed to triangular trigonometry, where we're talking about triangles. We will also deal with triangular trigonometry later on in the unit. But coordinate trigonometry deals with angles drawn on the coordinate grid, the xy axes. Okay? And we have a set of rules here, because if I tell you to sketch a particular angle on the coordinate grid, I could get 26 different pictures. So we all agree on how these things are drawn. What a rotation angle is, and we use the Greek letter theta to indicate a rotation angle. And anytime you see theta, it means, in this unit anyway, rotation angle. Remember that I told you a reference angle is different than a rotation angle, right? It's different. If I want reference angle, then I will put the following. And you may think that this is being very picky about the difference between these two angles, but it's crucial. Theta is the rotation angle. The reference angle is designated with the notation theta sub reference. You need to open up your... So how do we get a rotation angle? We take an initial arm, and you rotate it around a fixed point called the vertex. So if you look at my arm, if I take my arm, here's the initial arm, and if you're watching this on video, I'm sorry you don't get to see my arm. If I rotate it, but I keep my elbow in the same location, it ends up being in a different location. The arm is in a different location. This is called the terminal arm. Initial arm is where it starts, terminal arm is where it ends. My elbow is the vertex because my elbow is not moving. It's a fixed point. By the way, terminal arm is called the terminal arm because terminal means ending. When you land at an airport, the plane taxis to the terminal. That's where the term terminal comes from. However, that's not good enough, because if I said sketch an angle in standard position that's 40 degrees, and you sketched this, you sketched the following. And somebody else sketched this. These are different, aren't they? I mean, it's the same angle, but they look different. So we have this rule. The rotation angle is in standard position whenever the vertex is at the origin. So my elbow has always got to be at the origin, and the initial arm is on the positive x-axis. In other words, the initial arm is always in that position indicated by this diagram, and we rotate in a counterclockwise direction. That's important. I know that the first time I saw this, I kind of went, wait a minute, counterclockwise is the standard? Wouldn't we go clockwise? Wouldn't that make more sense? But the answer is no. Counterclockwise is the standard. And I want you to notice that the reason for that is that we will then sweep through the 4 quadrants in the order in which they are numbered. That's actually why we have them numbered that way. I don't know if anybody's ever explained to you. Why is it 1, 2, 3, 4 in those positions? Because in trigonometry, those are the orders, or that's the order that the terminal arm will sweep through as it rotates around the coordinate grid. All right. Warm up on the Cartesian coordinate grid, label the 4 quadrants. Well, I guess I've already done that up top, but we can do it again here. We're going to need room to write stuff, so I would label these in these approximate positions. There's nothing that says you have to use Roman numerals. You could write regular numbers if you liked. If you wanted to, you could write 1, 2, 3, 4. So those are the 4 quadrants. I know that you're taught this in grade 10, but you need to know it. You need to know this cold. You need to know where quadrant 3 is, where quadrant 4 is. For a lot of this work today, I'm not going to pause and ask if you have questions, but if you do have a question or a comment, let me know and we can discuss it. This is mostly just about presenting terminology. Label each of the following rotation angles in standard position. So, what does 0 degrees mean? It means that you take, and I'm not sure you want to draw this arrow, you take the initial arm that is always in this location, and the initial arm always has its vertex at the origin, and you rotate it counterclockwise, keeping the vertex in a fixed point. We rotate it 0 degrees. So this is what 0 degrees looks like. How do we indicate that? We put over here that this is 0 degrees. So I teach Math 30-1, and I know what's important in trigonometry in 30-1, and it's pretty much all of what we do here. So I want to start off by telling you, even at this level, that what I've done is I've labeled a position as 0 degrees. That position is 0 degrees. And I want to just maybe push the envelope a little bit. Not much, a little bit. Can somebody give me a different angle in standard position, a different number of degrees, that would have that same position? Kai, what is it? 360. So there's a difference between the destination, which is the location, and the number of degrees, which is the journey. How about this? If I told you that counterclockwise was a positive rotation angle, wouldn't it make sense that a negative rotation angle would be in the opposite direction? So that position could also be described as negative 360. Where would 720 degrees land? I'm getting off topic here, but that's okay. Where would 720 degrees land, Jack? Same as the 0, because 720 is going around twice, 360 plus 360. So I don't want you to think that this is always 0 degrees. Could be 36 million degrees, because 36 million is divisible by 360. 100,000 times or something. Whereas 90 degrees, well, again, you're not drawing these arrows, but if I rotate counterclockwise, I rotate counterclockwise 90 degrees, 90 degrees is up top on the y-axis. So this is 90 degrees. I hope, it might have been a while for some of you since you've dealt with any kind of degrees, but I hope you understand these are all multiples of 90 degrees, these 90, 180, 270, etc. 180 degrees would be to start at 0 and rotate 180 degrees around, which takes us to this point. That, by the way, would also be 540 degrees. You might have to use your calculator or crunch that number a little bit in your head. But 540 degrees, if I go 360 and add another 180, that's I think it's 540. Is it? Yeah. then I end up in the same position. 270 degrees, we need to go 90 degrees more in a counterclockwise direction. So this is 270 degrees. And then over here, I've kind of squeezed myself out, but this is also 360 degrees. Fairly straightforward, yes? Okay. C, and this is all about setting you up with the right set of skills and knowledge and terminology to be successful in the unit. What's the description of the angles that are included in each of the 4 quadrants? What can you tell me about an angle that's in quadrant 1? Well, it's between 0 and 90 degrees. And it may have been a while since you've seen that kind of notation. I want to talk about that for a second. First of all, I don't know if your Math 10 teacher really drilled this into you, but if it's degrees, you got to put a degree symbol there. You need a degree symbol. Otherwise, it's radians. So what does that mean? We have lots of time today. I want us to get off to as good a start as we can in this unit. Well, this has 2 statements in it. One of the statements, oh, that was dumb, is this statement. And one of the statements is this statement. So all we've done to get that one statement is we've said 0 degrees has to be less than the angle. Okay, think about that for a second. 0 has to be less than the angle. That means the angle is more than 0. This is saying that. And I know that not everybody gets this. If I told you that x was greater than 4, and you take that statement and you flip it over and read it backwards, this is what it looks like. 4 is less than x. So if 4 is less than x, x is greater than 4. So that's one of the things this is saying. It's saying that the angle is more than 0 and the angle is less than 360. This is saying the angle is more than 0. This is saying it's less than 360. When you put them together, it's like a run-on sentence, really, is what it looks like. Go ahead, Myron. Oh, it is 90. I'm using 360 as an example here. You're right. In our example, thank you. In our example, it is 90 degrees. Thank you. And I'll tell you why I'm fixated on 360. If you take a look at the main objective, this means 0 to 360. We're not going to be worrying about going past 360 or going into negatives. We're stuck with 0 to 360. And that's where my mind was, Myron, and I apologize. Okay. So we write in quadrant 1 that, there we go, that theta is wedged between 0 and 360. Can somebody tell me why I don't put the or equals to here? This is a bit of a subtle question I'm asking. Jack?
Because if it were equal to 0, then it wouldn't be an angle. Or it would be an angle, but it would not be considered a change in the terminal arm. So.
Turns out no, because 90 would be a change in the terminal arm. You almost had it. If it were 0, it wouldn't be something. Do you know, Thomas? What? Go ahead.
It's because if the degree was 0, it would also be applicable for quadrant 50.
And that leads to the way I would answer my question. If it's 0, it's not in quadrant 1. And it's not in quadrant 4 either. It's on the boundary. So the key is we want angles in quadrant 1. And as Thomas points out, if it were 0, we could say it's just as much in quadrant 4 as quadrant 1. But it can't be in two places at the same time. What about in quadrant 2? Well, it has to be between 90 degrees and 180 degrees. In quadrant 3, it has to be between 180 and 270. In quadrant 4, I guess it has to be between 270 degrees and 360 degrees. As long as we're only interested in 0 to 360. If we go past that, I mean, what I'm about to write is an extension of this course. You certainly don't need to know it. But you could put or you could write that. Like if you went around another 360, you'd be in a whole another set of angles. But again, I wouldn't be worried about that. Is 180 plus 360 540? Is 270 plus 360 630? Okay. I just wanted to check because sometimes my subtraction isn't right, my addition isn't right. So anyway, that's the warm-up. So now we have one more kind of layer of terminology that we have to talk about, which is called the reference angle. The reference angle is the smallest angle possible between a terminal arm and the x-axis. I'm not saying between the terminal arm and the positive x-axis. I'm saying between the terminal arm and the x-axis. So before we get to a specific example, if I told you that we had an initial arm that's here, which it always is, and the terminal arm is here, that would mean this is the rotation angle. Are you with me? If, on the other hand, I decided to rotate that further over to here, then this is the rotation angle. Still with me? I want you to notice that the rotation angles have a direction. There's an arrow on the end of that arc. If I had it, we might as well do all 4 quadrants. You will see this in an example, so there's no need to write this down. But if I had it now in quadrant 3, then this would be the rotation angle. So notice again, there's a direction to that, and I don't put any subscript. Theta is rotation angle. And I suppose we might as well go quadrant 4. In which case this is the rotation angle. You with me? We learned that already. The reference angle is the smallest angle between the terminal arm and the x-axis. So this is the reference angle. No direction. There's no direction associated with it. It's an angle. This is the reference angle. This is the reference angle. Do you remember me making a big deal at the beginning saying reference angle and rotation angle, just hang on, reference angle and rotation angle are different. And then I said, sometimes they might be the same. This is the reference angle here. So if that rotation angle, that brown angle that's showing a direction was 30 degrees, the reference angle would be 30 degrees. Go ahead, Jack.
So can it never be on the y-axis? It has to be on the x-axis?
It's always measured from the x-axis, yes. The terminal arm can be on the y-axis, but the angle is never measured to the y-axis. If we go to, and this is all good stuff. There's nothing here that is unimportant. If I were to take remember those 4 angles we talked about? 0 degrees was one of them. This would have a rotation angle of 0 degrees, and the reference angle would be 0 degrees. If it were up here, then the rotation angle would be 90 degrees. There's a direction. What would the reference angle be? It'd be 90 degrees as well, because the smallest angle between that arm and the x-axis is 90 degrees. If I put it over here, Jack, what would this rotation angle be? 180. And what would the reference angle be? It would be 0 because it's right on the x-axis. You're welcome. And down at the bottom, if the rotation angle terminated on the negative y-axis, the rotation angle would be 270 degrees. The reference angle would be 90. I just wanted to make sure that you weren't asking about that, and you weren't. But it's always measured from the x-axis. So now let's put this into practice with a couple of quick questions. Sketch a rotation angle of 60 degrees. So we're not going to get out a protractor, but you should understand that between my 2 arms is 90 degrees. And if we're rotating from this arm counterclockwise to 60, we have to rotate 2/3 of the way to 90. So, you know, I would say to you that if you had some kind of a written response and you drew that, I'm not going to give you the marks. And if you drew this, I'm not going to give you the marks. I have a way of figuring this out that we will talk about more later. I would say that is pretty darn close. And what you should probably do as well, although you don't have to, you should show the initial arm. You really don't have to, but what you definitely need to show is this. Theta equals 60 degrees. So Jack, I know you get this. So I'm not asking this to test you. I'm asking this to confirm. If the rotation angle is 60 degrees, what is the reference angle? 60. It's 60 degrees. And I hope that all of you see that if the rotation angle is in quadrant 1, the reference angle will be whatever the rotation angle is. And I tend to use the same colors. But again, I want to point out to you that the rotation angle has a direction to it, but the reference angle is just an angle. And the rotation angle doesn't require a subscript. We just write theta. So we've sketched it. What is the reference angle? I've labeled it on the diagram, so we're done. You may not think it's a big deal, but this arrow on here is really important. Bless you. Number 2, sketch a rotation angle of 150 degrees. So I want you to use your calculator and all your knowledge of where 0 is, where 90 is, where 180 is, etc., to decide how best to sketch this. Like how, we know, I hope it's in quadrant 2. It's going to be in quadrant 2. But where in quadrant 2? Is it halfway? Is it closer to one axis than the other? And I would say, I'm going to draw it about there, that 180 degrees is over here. You can see that 180 degrees has to be what we get when we add the reference and the rotation angles together in this case. So it's going to be 180 minus the 150. And I will, so which is 30 degrees. I will tell you that this is the case in quadrant 2. In quadrant 2, this will always be the case. I have never been a fan of memorization. I like to visualize things if I can. But that doesn't mean everybody is like me. So if you want to memorize this, in quadrant 2, this is the relationship between the reference and rotation angles. In quadrant 1, what's the relationship between the reference and rotation angles in quadrant 1? They're the same, right? All right, what about this one? I think you see where this is going. I'm going to sweep through all 4 quadrants. 225 degrees. I would like you to use your mathematical prowess to determine which quadrant that's going to be in and like where you should draw it. Which axis is it going to be closer to? The first thing I note is that 225 degrees is between 180 degrees and 270 degrees, so it's in quadrant 3. The next thing I would do, personally, is I would take 225 minus 180 in my head or on the calculator to find out how much past 180 I have to go before I stop. And I believe when you take 225 minus 180, you get 45. Then I'm going to use my knowledge that 45 degrees is half of 90, which means that this rotation angle will terminate halfway between those two axes. In other words, halfway between the axes is kind of a weird thing to say about angles. In other words, it's just as far away from the x-axis as it is from the y-axis. This, of course, would be the rotation angle. Direction, theta equals 225. The reference angle, well, we can take 225, and if I want to know what this is the reference angle. I'm going to have to take 225 and subtract this 180 to be left with the reference angle. So in this case, we're going to have 225 degrees minus 180. And I know that some of these numbers are fairly obvious looking at the diagram, but they're not always going to be nice numbers. It's 45 degrees is the reference angle. In quadrant 3, the reference angle is the rotation angle minus 180. And I want to point out something to you. When I was particularly in junior high, I learned very quickly that sometimes when I solved the problem, I would subtract the wrong way on my calculator. Do you know what I'm talking about here? You have to subtract, and then you'd subtract the wrong way and you'd be looking at a negative number. And then I would simply go, oh yeah, but I must have subtracted the wrong way, so I'm going to ignore the negative. How many of you know what I'm kind of talking about here? And then I realized that that doesn't mean it always works this way. Look at how you find the reference angle if it's in quadrant 2, 180 minus theta. In quadrant 3, it's theta minus 180. And you would get different answers. They wouldn't even just be negatives of each other. You get incorrect numbers if you subtract the wrong way. Finally, in quadrant 4, and I suspect many of you right away could tell me what you do to the rotation angle and the reference angle in terms of their relationship to each other. But let's sketch this first. 310 is, well, the first thing that pops into my head is it's 50 degrees away from 360. How many of you, I'm just curious, how many of you look at that 310 and go, it's 40 degrees past 270? Okay. If you do, then be very careful. It's going to look approximately like that. Be very careful that you don't drill, write this down first, theta equals 310 degrees, that you don't drill into your head that 40 degree angle, because the 40 degrees is not the reference angle, right? So you may come up with the 40 degrees as part of your sketch in your head, but the reference angle is actually 50. And that would be 360 degrees minus the 310 degrees, which is 50 degrees for the reference. Which means the reference angle, if the terminal arm lies in quadrant 4, will always be 360 minus the rotation angle. So in the end, when I use the angles that I know about, 0, 90, 180, and 270, when I use those to find out where to draw it, I never ever really use the 90 and 270. I always use 180 and 360, because then I'm thinking about a reference angle. Any questions with 1 through 4? I think I've done a fairly decent job of explaining this, so I'm going to give you a minute or so to come up with the 4 different rotation angles that are possible if we have a reference angle of 32 degrees, and I want you to sketch them. So the only hint I will give you is the only way you can get 4 different rotation angles, if the reference angle is the same, is that they're in the 4 different quadrants. So you need to sketch a reference angle of 32 in each of the 4 quadrants and determine the rotation angle. And that's the extent of the lesson. There's really not much to it. When I sketch these, everybody, I'm not going to sketch the initial arm. And I'm not going to worry about exactly where it is. I suppose I could get out a protractor and check to see how close I got. Not even close. I'm at 40. But, I mean, geez, I'm bang on 40 degrees for all of these. Who knew my estimation was that far off? And you don't need a protractor. Don't get me wrong. I'm not glamming these up for any particular reason other than I would like to have them a little more accurate on the video. I'm not the best at subtracting angles for some reason. Sometimes I get an extra 10 degrees somewhere. But if it's in quadrant 1, clearly the rotation angle is 32. What was the 32-degree reference angle, wasn't it? Was. If it's in quadrant 2, then I'm looking at that diagram saying if I take 180 minus 32, I get the rotation angle. Is 180 minus 32 148? If it's in quadrant 3, 180 plus 32 would give me the rotation. Is 180 plus 32 218? And if it's in quadrant 4, I could take 360 minus 32 and get 328. I'm sensing something from the masses here. Did I write something down wrong?
Yeah, that's between 2 and 12.
Oh, 212? Thank you. Was that what you guys over here were kind of wondering too? Yeah. My brain slipped a little gear there for a second. Plus 32 gives me 212. Thank you, Myron. That's it. That's all you need to really know for today. Quadrants, rotation and reference angles, and how they are connected to each other. So in your textbook, there are some questions you can use for practice to make sure you understand things. I'm going to hand back your exams, and you can take a look over them. I don't think I've had any of you as students before, but I'll let you know. I don't stand up here and go through an exam question by question. I think that collectively is a waste of a lot of people's time. If you feel that you need that, then we can certainly do that at lunch or something. But if you are going to do corrections because you need to learn from that, then you do them on a separate sheet of paper and staple them to the exam at the end. So I'll hand those back. You guys get to work, and then, man, we're just about done for the day, another 25 minutes or so.